Welcome to our lecture line, and another way of looking at a derivative is in terms of the limit. In the limit, that's a term you'll hear a lot when you start studying derivatives and calculus, and so let's explore that a little bit. Again, keep in mind that the derivative of a function is represented by the slope of that function. For example, here I have the equation y of x equals the quantity x minus 2 squared, which is equal to x squared minus 4x plus 4. The reason why I wrote it like this, it makes it a little bit easier to graph. So that means it's the parabola, and you know that the vertex then is moved to the right 2 units, like right there. So that's the equation, or that's the graph of that equation. Now, what you can say is that at different points along this graph, let's say if you take this point right here, the slope is negative and very steep. Here it's still negative, not quite as steep. Over here at the vertex, notice the slope is 0. That's an important fact that we'll use later on when we continue studying calculus. At this point right here, you can see that the slope is positive, and the more you go up on the curve right here, you see that the slope continues to be positive and gets steeper and steeper, steeper. So in that case, you see that the derivative is negative on this side and it's positive on that side. It's very steep here and it's very steep there, becomes less steep, goes to 0, and then on the positive end. Again, remember the derivative is equivalent to the slope of a function. It means how fast the dependent variable is changing with respect to the independent variable. X being the independent variable, y being the dependent variable. But how did we figure out how we can describe that in an equation format? So what we did was to say, okay, let's take this point right here, and let's try to figure out what the slope is at this point. And of course, if you draw the tangent line, a straight line that touches this curve right at that point, you can see that the slope of that tangent line is exactly equal to the slope of the function at that particular point. But of course, only at that point. You can see that the slope would be different over there, and of course, different over there. Now, if we imagine there that this point right here is the x position. Let's call it just x. So the value of that x coordinate right there is called x, and then the value of the y coordinate is simply the function evaluated at x, and so we call this f of x. So x is the x coordinate of that point, and f of x is the y coordinate of the point. So we can imagine that this point right here can be represented by x comma f of x. So x is the value for x, whatever it may be, and then f of x would then be the value for y calculated when you plug in an x. For example, if x is equal to 1, then you have 1 minus 4 plus 4, so y would be equal to 1. So that's simply the value for the function at that point. So now let's take another point a little bit further up the graph, this point right here. And so let's now imagine that we traveled a certain distance, delta x to the right, a small amount of distance, and that means that the x value for this point now would be x plus the amount of distance that we traveled, x plus delta x. And what would be the corresponding y value of that point? Well, again, we're going to evaluate that function over here, and then the function would then be equal to f of x plus delta x, like that. So the coordinates of that point, let's write that down, the coordinates of that point would be x plus delta x for the x value, and for the y value it would be f evaluated at x plus delta x. Now, if we draw our usual triangle, connecting these 2 points like that, you can see here that this here is the change in the y value between those 2 points. And this, of course, we already know that that's the change in the x value, delta x. So the change in the y value, that would be equal to what the value is up here, which would be f of x plus delta x, minus the value over here, which would be f of x. So that would be the change in the y value. And this, of course, here's the change in the x value. And now remember that the slope of that line, which is equal to the change in the y value divided by the change in the x value, can now be written as f of x plus delta x minus f of x, and the whole thing divided by delta x. So that would now be a good representation of the slope of this line right here. Now, if I draw the slope of this line, I would get this slope right here. And notice it's not exactly the same as the slope of the tangent line, so it's not a true representation of the slope at that point. It's just the average slope going from that point to that point. So not quite the same. Notice that slope is like this, and this slope is like this. So how can I get this slope to be closer to the slope of the tangent line? Well, I can do that by moving my point a little bit closer. For example, if I now say instead of having the point way out there, I make my delta x smaller. I bring it over there. And so now this would be the slope there. Note that would be my triangle. Now this would be my delta x. That would be my delta y. Exactly the same, except they're smaller now. And notice that the slope of that line right there is closer to the slope of the tangent line, but still not quite close enough. So what I'm going to do is make it even smaller. So I'll bring my point even closer, like right there. Draw a new little triangle. And notice that the smaller I make that triangle, the closer the slope of the hypotenuse of that triangle will be equal to the slope of the tangent line touching upon that point. So you begin to see then, if you make that triangle really, really small, very tiny, infinitely small, so that the delta x goes to 0, the slope of that hypotenuse will be exactly equal to the slope of the tangent line, and that would then be the derivative at that point. So that means in the limit when delta x goes to 0, and that's where the term comes from, in the limit. But one problem though, what happens when you let delta x go to 0? Now you're dividing by 0. But then the numerator will also become so small. If delta x goes to 0, the numerator will go to 0 as well. So we have kind of like a 0 divided by 0 condition, which of course normally is undefined. But what we do is we don't quite go to the point all the way where delta x is 0. Very, very close. The closer we get, the more we're going to get the exact ratio representing the slope of that line. And that's what we mean by definition, that the slope, the derivative, is now defined as the limit as delta x goes to 0, get really, really, really close, almost infinitely close, but not quite 0, of the function of that would be the delta y divided by delta x, the ratio, of course, that represents the slope, which can now be written as the limit as delta x goes to 0. Instead of writing delta y, we'll write this right here. So that would be equal to f of x plus delta x minus f of x divided by delta x. And of course, in the limit, when this goes to 0, that will represent the slope of the curve at that point, which is, of course, the derivative of that function. All right, again, just to make sure you remember that this right here is simply a delta y. That's simply this value right here. And of course, it gets smaller, smaller, smaller. So your triangle gets smaller. And the delta x is this right here. And of course, the ratio of the rise over the run is the slope. So what we're going to do now is we're going to take this function right here and calculate the limit as delta x goes to 0 of this quantity for that function. You see how that works. All right. So first of all, if we want to take the derivative of this, y prime as a function of x, which is equal to dy dx, that's called the derivative of y with respect to x, it's going to equal to the limit. Whoop, didn't write the limit very well here. The limit as delta x goes to 0 of f of x plus delta x. So what we're going to do is we're going to take f of x, that's this function right here, and so this can also be written as the function with respect to x. And instead of x, we're going to write x plus delta x. So everywhere we see an x, we're simply going to replace by f of x plus delta x. So we get x plus delta x, quantity squared, plus, not plus, minus 4 times x plus delta x, plus 4. And let me put brackets around it, because this is that right there. It's the function evaluated at x plus delta x. It's the function evaluated at a point a little bit further away from my initial point. Of course, in the limit, we're going to make that point really, really close together. Minus the original function. So the original function is simply x squared minus 4x plus 4, and the whole thing divided by delta x. And if I take the limit when delta x goes to 0, that should represent the derivative. Again, you sit there and go, well, wait a minute. When delta x goes to 0, I have a 0 in the denominator. I can do that, but wait, something interesting is going to happen. Let's first multiply this out. So this is equal to the limit as delta x goes to 0 of, this becomes x squared plus 2x delta x plus the quantity delta x squared minus 4x minus 4 delta x plus 4, and let me give myself a little bit more space, minus x squared plus 4x minus 4, and the whole thing divided by delta x. Now, the fun part. What you'll find when you do this is some things are going to cancel out. We have an x squared and a minus x squared. That cancels out. My red pen is kind of dying on me. Do I have a better red pen? Let's try this one right here. So this cancels out with that. That's better. Then I have a minus 4x and a plus 4x, so that cancels out. And a plus 4 and a minus 4, that cancels out. So when I cancel all that out, what do I have left? So that means that the derivative, the dy dx, is going to be equal to the limit. And you have to keep writing this, otherwise it's not correct. When delta x approaches 0, of, and see what's left. 2x delta x plus delta x quantity squared minus 4 delta x, and the whole thing divided by delta x. Now notice that in the numerator, every term has a delta x in it, which means I can divide the denominator into the numerator, which means this is equal to the limit as delta x goes to 0. And here, the delta x cancels out of 2x plus delta x minus 4. Notice there's no longer a delta x in the denominator. Now we can actually go take the limit. I can now allow delta x to go to 0 without having a violation of having 0 in the denominator. So when I take the limit, when I let delta x go to 0, this simply drops out, and this becomes 2x minus 4. And this then becomes a derivative of the original function. What does that mean? Well, notice it's a function in itself. Here we have, let me rewrite it, dy dx, which is the derivative, is equal to 2x minus 4. Remember, that represents the slope of the original function. Notice, when x becomes a negative number, you have a negative slope. When x becomes a positive number, a big positive number, I should say, then the slope becomes positive. So when x becomes larger than 2, 2 times a number larger than 2 will become, minus 4 will become a positive number. So notice that now this represents the slope anywhere along the curve. Give me a value for x. When x is 0 right here, then my slope is negative 4. When x is 2, my slope is 0. When x is positive 2, positive 4, my slope is positive 4. So you can see that now I have an equation describing the slope anywhere along the curve, which by definition is the derivative of that original function. That's what a derivative is.